All right. Good day. Again, we're back with our paper review sessions so that we are able to do adequate revisions for our papers. This is Krazifizix, Maths and Science Clinic. You can check us on www.krazifizix.org.za. Send us an email, info@krazifizix.org.za. Go to YouTube, www.youtube.com, and search for Krazifizix. You'll get more videos. Facebook, Krazifizix, you can check on our page. You would also have info. Give us a call, send us a WhatsApp or an SMS, and we will be able to get back to you. Now, today, we're looking at February, March 2018. And this is the supplementary exam. So we're going to run through this paper from beginning to the end. And I want you to actually be able to run through this paper with us. All right? So you have the paper. You can check on the department website to get a copy. Get a copy of the paper and run through with us. We would run through the multiple choice and the structured questions. We're going to be fast, so you got to be fast as well. However, you have the chance to rewind and play over again if there is something you did not understand. So February, March, paper 1. Here we go. Question 1.1. A constant horizontal force F is applied to a box resting on a horizontal frictionless surface. All right, look at the word friction. Which one of the following statements regarding force F is correct? Force F will cause the box to move with. Now, this is basically asking us for Newton's second law. If you remember your Newton's second law, what does your Newton's second law state? Your Newton's second law states that when a net force acts on an object, the net force will cause the object to accelerate. Now, if we say something is accelerating, what does it mean? It simply means velocity is changing per unit what? Time. Automatically, what does this tell us? My velocity is changing. All right, velocity is changing. If velocity is changing, what are the things that will change? Number 1, kinetic energy would change, because kinetic energy is half mv squared. Number 2, momentum will change, which is equal to what? Momentum is mass times velocity. So these two will change because velocity is changing. Let's go to our options. Velocity cannot be constant because we're talking about acceleration. Kinetic energy will be changed as well. Momentum will change. Newton's second law, the net force will cause the object to accelerate. Constant acceleration, 1A. Done. Newton's laws. Now you need to learn how to remove options from your multiple choice. All right. Now let's go ahead to question number 0.2. Question 1.2. Question 1.2. All right. A block rests on a table. The table stands on a concrete floor. The normal force is represented by N, as shown in the diagram. Remember, your normal force is always perpendicular to the surface. Which one of the following forces will form an action-reaction pair with the normal force? Action-reaction pair with the normal force. That's your Newton's third law. That if object A exerts a force on object B will what? Simultaneously exert a force on object A, which is equal in magnitude and opposite in direction. So we're using Newton's what? Third law. Okay. Now, which one of the following will form an action pair, action-reaction pair with the normal force? What is the normal force? In this case, the normal force is the force exerted by the table on the block. Okay, so Table on the block, normal force. The block will also exert a force on the table, which must be equal. So we're talking about block on table. Let's go check our options. Force of block on the earth, no. Now again, the two forces must be in contact, except for your electrostatics. But in this case, we talk about contact force. Force of block on the table. We get our answer. But let's try to cancel the other options. Force of table, surface on the block. This is your normal force, and that's what the question is here, so we cannot repeat this. Force of block on the concrete. Now the block is not on the concrete, so the block is not actually exerting a force on the concrete. So our correct answer is B. We get it right? So action-reaction pair, Newton's third law of motion. All right. Question number 1.3. A small stone is dropped from a height y above the ground. It strikes the ground after t seconds as shown in the diagram. All right. This is a free fall. Why is it a free fall? Let's define quickly. A free fall is an object that experiences the force of gravity alone. All right, we have different definitions, or you can say an object that has only the force of gravity acting on it. Object that has only the force of gravity acting on it. And also here we can actually say it is a conservative system, or what you know as isolated system. We'll do mention this again when we get to work. All right, now take upward as positive direction and the ground as 0. Okay, now if the object is dropped, that means the object is coming down. Okay, if the object is dropped, it means the object is just coming down. Let's try to find our answer first. Object is dropped. Now remember, this is time. We want which one of the following diagrams shows the position? All right, the position. Now guys, it's not going to come down straight like this. It's wrong, because if you do this, it means time is the same. So this is wrong. What we actually do is this. All right, let's sketch. If the object is dropped, the object is going to move this way. All right, this is how the object is moving. It's dropped from a height, so it's dropped from here, and here is the ground. Now you have your sketch like this. Here's the ground. The question says use the ground as your 0 reference. What you do is you go to the ground and draw your x-axis there, 0 reference. Draw your x on the ground, and then the point where the object starts from, draw your y, and you have your position time graph. Simple. What option do we have? Let's check our options quickly. What options do we have? Our option is C. Correct. Our option is C, because the object moves exactly that way and hits the ground there. Correct option is C. I hope we get that that's vertical projectile motion. Now let's go to question 1.4. Question 1.4. All right, here we go with question 1.4. This is momentum. We can quickly see that. Let us perform an experiment using identical trolleys, each of mass m. The trolleys are arranged as shown on the diagram below. They are initially at rest on a frictionless surface. Again, we're talking about an isolated system. Now the law must actually quickly come to your memory, and are connected with a compressed massless spring. When the spring is released, it falls vertically down, and the single trolley moves with a momentum p to the left. All right. Remember now, momentum is a vector quantity. The magnitude of the momentum of the two trolleys. Okay. Now, what do we need to think about here? The law of conservation of linear momentum. All right. The law of conservation, which says that the total linear momentum before should be equal to the total linear momentum after. So let's expand this bracket. Now these objects are together, so I can say m1 plus m2 with the same velocity because it's one object. It's separate here, m1 vf1 plus m2 vf2. Now this is what we know. M, my first mass. By the way, let's take right, because it's momentum, right as positive. So I'm going to have m plus 2m, and that should give me my initial velocity 0 because it's at rest. Now they told us that the other one moves at p. The small mass moves at p. That means the momentum here is equal to p. Now what is the momentum here? We're just going to leave this like this. Let's leave this like this. M2. Remember now that this small one moves to the left, so we should have a negative p there. Let's write this carefully. Negative what? P. Let's solve this. Negative because it's moving to the left. The whole of this would give me 0 equals to negative p plus the momentum of the second object. Let's move this over to the other side. What is this? P equals to what? m2 vf2. That means my second momentum is also p because momentum should be equal to 0. That's my answer there. P. All right. So this is your law of conservation of linear momentum. Good. Question 1.5. Please rewind over and over again just to make sure you get the concept on every question. It's very, very important that we answer multiple choice questions correctly. All right. Question 1.5. A pendulum bob is released from rest from point P, released, all right, above a horizontal surface. At the lowest point Q of its swing, it collides with a stationary block, right? That's my block there, on a frictionless horizontal surface as shown below. Ignore air friction, isolated system. Which one of the following combinations of conservation laws can be used to calculate the speed of the bob at Q immediately before and after collision? Now let's check. They said conservative laws. Which laws should we be thinking about? Conservation of mechanical energy. All right, we will state this later on. And conservation of linear momentum. Remember that both of them are in isolated system. I can simply use this when I talk about collisions. Is that all right? So number one, let's check our options. Before and after collision. This is wrong. All right, this is wrong. So we are only left with option A and D. All right, but let's look at speed at Q. Speed at Q. How do we calculate the speed of pendulum bob P moving down? Guys, there's a height involved here. Once you have a height, then you'll be talking about what? Mechanical what? Energy. Because mechanical is the sum of your kinetic and potential. And what is potential? mgh. So we could look at the conservation of mechanical energy from the top there. And then conservation of what? Linear momentum. All right, 1.5, our answer is A. We get that, right? Mechanical because there's a height, mgh. And then linear momentum because we talk about collision. So our answer is A there. All right, let's run to question 1.6. 1.6. Which one of the statements below about Doppler effect, all right, we're talking about Doppler, which is waves, is correct? The Doppler effect is only applicable to sound waves. That's not true. Light is also involved. Light is also involved, so that's not true. because we can talk about our red shift and our blue shift. That's wrong. The Doppler effect can be used to explain that the universe is expanding. Okay, that's correct. That's true. Electrons are ejected. No. Electrons are not ejected on Doppler effect. This is wrong. Electrons are ejected when we talk about photoelectric effect. All right. Photoelectric effect. So this is wrong. Stationary listener hears a lower pitch of the sound from the siren of an approaching. If it's moving towards, it's supposed to go higher. This is wrong. So the correct option is what? B. 2 marks. The magnitude of the electrostatic force Q1 due to another Q2 is F. Now what should come to your mind quickly is F equals to K Q1 Q2 over R squared. Now let's say this is our F old. Let's just put it like that for simple understanding. Both charges are now doubled, which means I have a new force. And that new force, let's check now, would be K. Remember my Q1 is now doubled. I'm going to have 2 Q1. Both charges are doubled. I'm going to have 2 Q2. Okay? Without changing the distance between them, my R squared. Let's solve this. 2 multiplied by 2 would give me 4K Q1 Q2 over R squared. Do you notice that this now is equal to my F old? So what am I going to have? My F, new F now, will be equal to 4F, the old force, 4F. And my answer there is C. Correct? Good. You need to understand this because this is also applicable under universal gravitation. Now let's run to 1.8. Almost done with our multiple choice. And I hope this has been helpful to you. All right. Multiple choice is not time where you play picky money more, you know. Let us do my mother like rice, I like beans, but my father doesn't like any. And wherever they end, they guess. 4 identical bulbs, P, Q, R, and S, are connected to a cell in a circuit as shown below. The cell has negligible internal resistance. All right, so we have this 4. We have this 4 here. We have this 4. What do we know quickly? One thing we need to understand is that there's an acronym I use. I say South African Police Department is paid. All right. And what we simply mean is series are potential dividers. Series are potential dividers. Parallel are current. Remember, current is I. Current what? Dividers. Okay. Now let's check something here. Current is going to come through this way, move through P. So we have total current going through P. What happens here? These two are connected in parallel. So what happens? Current here is divided. So I'm going to have I over 2 and I over 2. Why? Because they are the same. All right. And then what happens here? So current comes there. What happens here? Total current. So the current in I, the current in P, and the current in R are the same. These two are going to shine at the same brightness, which will be more than S and Q, because here I have what? A low current here. So P and R will shine the same way, more than S and Q. P will burn brighter than R. That's not true because they have the same current, the same potential difference. S and Q will burn brighter. That's not true because our current there is actually divided. All right. And the potential difference also has a play. Now P and R and these two resistors are connected in series. So number one, they've divided potential difference equally. All right, so they have the same potential difference, but current is not the same. P and R will burn brighter than S and Q. Yes, that's what we said. All the bulbs will burn. No, they cannot because they have different current flowing through them. All right, correct option is what? C. South African Police Department is paid. 1.9. Which of the following energy conversions takes place when a DC motor is in operation? What does a motor do? A motor converts what? Electrical energy to mechanical energy. That's the job of a motor. Now that you must just know quickly. A motor. Alright, so the correct answer, electrical to mechanical, and you're done. Simple. Get your 2 marks and move away. The last one. In an investigation of the photoelectric effect, the graph of maximum kinetic energy versus frequency was obtained. All right, look at the intercepts P and Q represent. Let's do something here. This is mathematical here. All right, this is mathematical. Now check this. This is a straight line graph. What's the equation of a straight line graph? Y equals to mx plus c, where this is my gradient, all right, and this is my y-intercept. Now, what is the formula? This is photoelectric effect. The formula that needs to come to your mind is E. Go to your formula page, you'll get this. Work function plus kinetic what? Energy. Okay, let's check something. Kinetic energy is on my y. I need to rearrange this equation to look like this. So since kinetic energy is on my y, can I make kinetic energy my change of subject now? Let's do that. If I move this here, what am I going to have? E minus work function equals to kinetic what? Energy. Let's write this nicely now. Kinetic energy equals to E minus work function. Now, do you see that here I already have Y as kinetic energy? Now, what's on the X? Frequency. Where am I going to get frequency from here? Do you remember again on the formula page that the energy of the photon can be calculated as HF minus work function, EK. Oh, we're there. Let's compare. Y equals to mx plus c. Okay. On my y, I've got kinetic energy. That's sorted. On my x, do you see it's right exactly where I want it to be? Frequency, sorted. So what does it mean? My m, which is the gradient, is my Planck's what? Constant. Gradient is Planck's constant. And then my y-intercept, which is c, becomes my work function. And you would see here it's a negative y-intercept. So let's come back here. This is my y-intercept. It's a negative work function. Are we there? All right. And this one now, I'm talking about frequency. But this one now becomes my threshold because it's frequency. Threshold because that's what's on my x. Threshold frequency. Let's go check our options. Although we know, we're learning here, h equals to Planck's what? Constant. So let's go see what the question wants us to do. The intercept P. What is P? Work function. Q. Threshold frequency. P. Work function. Q. Threshold frequency. We're correct. So this is how to interpret. So here, this is how to interpret your graphs, your physics graphs, especially if it is a straight line graph. You need to use this on motion, use this on electricity. Anything that has a straight line graph will just work well with this. And I think we would see this as we go on in the question. So multiple choice done. Please rewind, because in doing multiple choice, we answer quite a whole lot of questions. Now let's run through our structured questions as fast as we can. So here we go. Question number 2, Newton's laws. Grade 11. So if you're in grade 11, this is actually beneficial for you too. All right. It says 2 boxes P and Q resting on a rough. Now when you see rough, guys, when you read your questions, please have a pencil where you underline, because now you are identifying forces, rough, horizontal. So that tells us that there is what? Friction there. Let's make this. So here, number one, we know there is friction, all right? It says surface. It means there's normal, because normal force is the force exerted by the surface of the object, and it is perpendicular to the surface. So already we have two forces. Where would that help us? That would help us when we draw our free body diagrams. They are connected by a light, inextensible string. What force are we talking about? Tension. The boxes have masses 5 kg and 2 kg respectively. A constant force F acting at an angle of 30. All right, acting a constant force F. What are we talking about? Force applied on the 5 kg, as shown in the diagram. The two move at constant speed of 2 meters per second. 2.1. State Newton's first law of motion. Guys, we need to know our laws. A body will remain at rest. A body or an object will remain at rest or motion at constant velocity, or use the word uniform. Constant velocity, all right, unless a non-zero resultant force or net force acts on it. You need to practice this over and over again. All right, a body will remain at rest or continue in uniform motion unless a non-zero resultant force acts on it. You get your 2 marks there. Draw a labeled free body diagram for Q. Now let's look at our Q. Let's interpret. What forces do we see on Q? Number one, there is a normal force because the object is on a surface. How do we represent? Please use a ruler when you draw. So here I've got my normal force, right in full, normal force. Okay, Q has a mass, so obviously it has a weight. All right, so I am going to now call this my weight, or what you know as the force of gravity. Now there is a rope here, okay, there's a string here, so we talk about what? Tension. And you would notice that P is actually pulling. So my force is this way. Q is being pulled. Do you see the arrow there? Arrow there. And with that, it's pulled with my tension. But we talk about what? A rough horizontal face. So there's friction. Please get the definition of friction very well. Friction is the force that opposes motion, and it acts parallel to the surface. All right, so my friction would be like that. Okay, but it should be a bit shorter because the object is now moving. Kinetic what? Friction. You have your 4 marks involved there. Quickly, that's good. 4 marks. These are free marks for every learner. All right, free marks there. Now let's look at 2.3. Calculations now. 2.3. Box P experiences a constant frictional force of 5. It is always good to write what we know. What is our frictional force? Our frictional force is what? 5 newtons. All right, frictional force on P. In box Q, frictional force is 3 newtons. Good. Calculate the magnitude of force F. All right, 6 marks, guys. We need to do this diligently. Now, because we're dealing with Newton's laws and motion here, when a net force acts on an object, the object will accelerate in the direction of the net force. All right, now let's deal with Q quickly. Remember, we have our free body diagram on Q. Let me just draw it quickly. Now it's a simple sketch because already we have the correct diagram up there. We have friction, we have what? Normal, we have the weight, and we have what? Tension. Now, how is the object moving? The object is moving to the right, so I'm going to use my horizontal forces. Because I'm dealing with forces, I'm going to pick the direction of motion as positive, which means tension is positive and friction is what? Negative. All right, I'm dealing with horizontal movement, hence I'm dealing with horizontal what? Forces. Okay, now F net equals to MA. Let's see what we can get from here. Tension plus, because it's net, we said plus. Tension plus negative what? Friction equals to MA. Tension plus negative friction equals to MA. Now remember, the question says at constant speed. If it is constant speed, acceleration therefore should be equal to 0. At constant speed or constant velocity, acceleration is equal to 0. That's a very important key that we need to know. Let's see, can we substitute tension minus, we do know, remember guys, this is Q. We know our friction here, which is 3, equals to 3 multiplied by 0. T therefore equals to, this is 0. Move this over, we have 3 newtons there, tension. But we're not really looking for tension. It will help us calculate the other one. Now let's go draw the other object. The other object now is P. Other object is P. What do we need? Let's draw a free body diagram quickly. Guys, you cannot work effectively without a free body diagram. That's my force. All right, what do I have there? My normal. What do I have? My weight. And in this direction, I've got 2 forces. I've got my tension and I've got my friction. All right, guys, this is quite important. We need to learn how to resolve. Now, I'm going to use a red ink here just to show us the resolving. Let me clean all of this for clarity. Here, I've got my horizontal and my vertical. All right, my vertical will be Fy and my horizontal will be what? Fx. Now, do you see that this gives you a right angle triangle? Let me export that triangle here. I'm going to have F, Fx, and this is what? Fy. Fy, F, and Fx. Angle 30. Now I can use my trig ratio. So here is my free body diagram, which is okay. All right. But to calculate, I'm going to draw another diagram. So I'm going to have 2 forces acting upwards, 1 force acting down, 2 forces acting, parallel forces acting in this direction, friction, tension, weight, Fx, normal, or Fy, and normal. That's my new free body diagram. All right. So what is my Fx? Because the object again is moving horizontally. Let's use our trig ratio here. What is cos 30 going to be? Why am I using cos? Guys, I know this as my hypotenuse. I'm looking for this, which is what? Adjacent. Remember, this is opposite. So what is my cos 30 is what? Adjacent, which is Fx, over hypotenuse, which is what? F. I hope you got that. Cross multiplied. Fx now equals to what? F cos 30. So this is my F cos 30. Again, it is moving to the right, so this is what? Positive. These two are going to be negative. All right, so let's now work. All right, my Fy would be F sine 30. Again, if you use your trig ratio here, sine 30. Okay, so let's go on. I hope you got that. Please rewind that over and over again till you are able to calculate that. Now I have Fx plus, okay, let's do this. F net equals to MA. All right, which is Fx. I want you to see the diagram. I want you to be able to see my diagram first. Fx plus negative tension, I'm sure you know where the negative is coming from, plus negative friction equals to what? MA. Okay, so let's do this together now. Let's try to substitute together. This is F cos 30, all right? What's my tension? Negative 3. What's my friction? Negative what? 5. We're given that in the question, if you remember. We're given that in the question. It says block P experiences a frictional force of what? 5. And that is equal to, what is the mass here? 5. And acceleration, constant velocity or constant speed, 0. Let's solve this together now. What are we going to have? F cos 30 minus 8 equals to 0. F cos 30 equals to what? 8. Divide both sides by cos 30. Let's try to reduce the calculator usage. Now, if you do this on your calculator, you would be getting 9,238 Newton. But we must round up to 2 decimal places, which gives us 9,24. And then you have your marks. All right. Where would you have been marked here? Let's quickly mark this together. Let's mark this together. Where will the marks be? We're looking for 6 marks there. All right. Where did we start the calculation? All right. Let me use a red one. F net equals to MA. We get a mark there. All right. We get a mark for substituting 3. And we get a mark for substituting 0. How many marks there? 3 already. Where will we get the remaining 3? We'll get the remaining 3 when you do your resolving. F cos 30 minus 5 minus 3 should give you 0. You get a mark there. By the way, for doing this again, you get your mark because the formulas are now different. That's 2 marks, and then your final answer with a unit, you get the 6 marks. Done. 6 marks done there. All right. Let's look at question 2.4. What is the examiner actually trying to figure out here? The string connecting P and Q suddenly breaks after 3 seconds while force F is still being applied. Let us draw the velocity time graph of the motion. All right, let us draw the velocity time graph. Okay, and we have this graph. Now, the first question says, write down the time at which the string breaks. What do you know? The string is actually creating a force. When the string breaks, what are we expecting? We are expecting a decrease in force. So the string breaks at 3 seconds. So my 2.4 is what? 3 seconds. That's where it breaks. Which portion X, Y, Z of the graph represent the motion of box Q after the string breaks? Guys, if we remove the applied force, automatically what happens? The velocity decreases. All right? Velocity decreases. All right? When velocity decreases, we are going to have what you call a negative acceleration. Why negative? My final velocity now is smaller than my initial what? Velocity. Okay. So if velocity decreases, look at, automatically it's not Z. Automatically it's not X. It has to be Y. But the question says, use the information on the graph to fully support your answer. Number 1, velocity decreases. We can see that there, decrease. All right, it decreases. Number 2, negative what? Acceleration, because now my VI will be greater than my VF. And remember, acceleration is what? VF minus VI over what? Delta T. Great 10. And number 3, because it's 4 marks, all right, we can also now say that this is because the net force acting on Q, all right, is in the opposite what? Direction. Why are we saying it's in the opposite direction? Guys, you do have this. You have Fx, all right, on Q. On Q, not on Q, we don't have Fx. On Q, we have what? Tension this way, and we have what? Friction. Now, if the rod snaps or breaks, what happens? Tension is no longer there. So our new diagram will just be this. Remember Newton's second law said the object will accelerate in the direction of the net force. But where is my net force? My net force is now opposite. That's why we said decreasing acceleration now. Decreasing what? Acceleration, or negative, because it is no longer in the direction of the net force. It's in the opposite direction of the net force. All right, so these are the three reasons you talk about. You get your mark for talking about the net force again. It's only friction, there's no more tension. So the net force is acting against the direction, hence it is decreasing. All right, that is question number 2 there. Done. Newton's second law, it's grade 11 concept. So this section is also good for our grade 11 learners. Rewind the video over and over again until you get the whole concept. Question number 3, vertical. All right, here we're going to do a whole lot of explanation. A ball is thrown vertically downwards from the top of a building. All right, it is thrown, so there's an initial velocity. Here again is a straight line graph. We're going to use our y equals to mx plus c from the top of a building, all right, and bounces a few times as it hits the ground, and you can see the graph. The VT, velocity time graph below, describes the motion of the ball from the time it is thrown up to a certain time t. All right, I actually advise that you need to be able to draw a graph from this question just by looking at it. Take downward as positive direction and the ground as 0 reference. The graph is not drawn to scale. Let's try to study this graph quickly. Graph not drawn to scale. It's fine. We'll be able to study this graph. Okay, I want us to study this graph and explain this graph. Now, where is my initial? Okay, this object is thrown. Now, do you see that velocity here? Let's use a red one. My initial velocity is 10. But what is happening? Velocity is increasing. Okay. Velocity is increasing. I don't make a joke here talking about an old woman who has missing dentition. Teeth are no longer there. Now, if she calls a window, now a window is spelled this way. But she doesn't call it a window because, she has missing front tooth. She calls it a findo, a findo. Now, she calls it like this, a findo. You know what this simply means? It means the velocity of an object will increase when the object is moving down, if it's a free fall. Velocity will increase when the object is moving what? Down, findo. So every time you see a window, do your vertical projector. Now, do you see that velocity is increasing here? So the only thing happening is that the object is moving what? Down. If I were to have a graph, check my graph. Let's draw. That's the ground. The object is moving what? It's thrown downward. So the object is moving down. This question was asked in the multiple choice. Let's label this point A, point B, point C, point D, point E, point F, and point G. I just want to show you something here quickly. Now, this is my point A where I started from. It stops there, hits the ground at point B. Now, let's check. They said take downward as positive. This is down. Do you notice now this C has jumped to my negative side, which is a change of direction? But what do we know? Look at the time frame here. It hits the ground at 2 seconds and leaves the ground because it's now negative, changing direction at 2,2. What happens? It means it spends a bit of time on the ground. It spends a bit of time on the ground. So the object is here. So I have my C here. So what happens to C? It's negative, right? Now what's happening to the object? It gets to point D. And the velocity here is 0. Velocity at maximum height. So that means the object changes direction and bounces up. All right? Reaches the maximum height, T. What happens here? It's now positive again. They said take positive as down. So every time it's on the positive side, it's actually going down. So D to E must be down. E reaches the ground. Again, check 7,71 second. And between 7,71 and 8, that's about 0,09 seconds. It spends a time again on the ground. All right. What do you notice about F? F is negative. Is that okay? Which means direction has changed. If down is positive, it means negative is what? It's going where? Upwards. And it gets to T, which is again velocity 0, maximum height. All right. So this is what? Oh, G there. So this is what? F, and maximum height, which is what? G. Maximum height, which is G. Guys, this is my sketch. This is my sketch. And you know what you have done with the sketch? You have actually drawn your position time graph. Let me show you quickly. Let's draw a position time graph using the ground as reference point. What do? I go to my ground on the graph and draw my x-axis using ground as reference. X and my y at the beginning. That's your position time graph. Just understanding the graph alone, you have drawn your position time graph by sketching. Somebody's asking, why is T lower than A? Why is G lower than G? Let's answer you quickly. Look at the velocity. Look at the velocity here. From 10 to 29,6. Is that okay? C. Now, we don't know C. But here, look at E. E is what? 27. Automatically, this also should be 20 what? 7. I'll prove it to you mathematically. All right. But why are we saying D is now lower? This object loses energy because it's an inelastic collision. Why am I saying inelastic? The velocity has decreased from 29,6 to 27, negative 27. So a loss in velocity means a loss of energy. So the object bounces but does not have the same energy again, so it will not reach the maximum height of A. Inelastic. Inelastic. And how do we know it's inelastic here? It stays on the ground. It is possible to still bounce up at the same time and still be inelastic because energy is what? Lost. All right. So D and G, the object keep bouncing, and that's what you have when you throw a ball down. It will not reach its maximum height again. The maximum height will keep reducing every time. Okay. Now let's answer the questions. I hope you got this quickly. Oh, great. Write down the speed with which the ball is thrown. Initial velocity. They said speed. My initial velocity. What's my initial velocity? My initial velocity, we can simply read that from there. It's 10 meters per second. 1 mark. Okay. 1 mark. Number 2. All the parts of the graph have the same gradient. Give a reason. Let's check something. Straight line graph. Y equals to mx plus what? C. What is the equation we're dealing with here? Vf equals to Vi plus A delta what? T. We did this earlier on under photoelectric effect. Now, what is on my y-axis? My y is velocity here. And what is on my x? Time. I need to rearrange this. All right, already, this is fine. I have that there. My time is my x. Look at what I'm going to do. Vf, I'm just going to shift this. A delta t plus what? Vi. Let's compare. Y equals to mx plus c. Now, that's on my y-axis. That's sorted. X on the time. That's sorted. So what do we know? My gradient equals to acceleration, and it's actually gravitational acceleration. Gravitational what? Acceleration. Of what? 9,8 meters per second squared downwards. What is my C from mathematics? C is my y what? Intercept. And what is that? My y-intercept. Do you notice now it's my initial what? Velocity, which also helps us to understand 3.1. thrown downwards. My initial is my y-intercept. Let's check the y-intercept. It's 10. Now let's answer this question. All the parts of the same gradient, because our gradient is simply acceleration due to gravity, and it is a constant. It is a constant. So what we're saying now is this: the gradient represents what? Represents gravitational acceleration, or what you know as acceleration due to gravity, which is what? A constant for a free fall, which is constant for a free fall, and that value is 9.8 meter per second squared. I want us to quickly try something. Let's try to calculate. Let me remove all of this so that it's clear. Let's try to calculate something here. Can we look at this section? Let's look at this section. Let's take this as 0.1 and let's take this as 0.2. What is gradient? M equals to y2 minus y1 over x2 minus x1. Now what is my y2? 29.6. What is my y1? 10. Over, what's my x2? It's 2. What is my x1? It's 0, because this is my point 1. Remember mathematics. All right. What will this give you? This will give you 19.6 divided by 2, and this would give you positive 9.8. Do you see my acceleration there due to gravity? Done. Meters per second squared. Meters per second squared. Again, let's do this. Let's do something here. This is my y. What's my unit? It's velocity here, right? So we're actually saying v2 minus v1 over t2 minus t1, because that's what's on my x. Now what's the unit here? It's meters per second over second, and this we can write as meters per second per second. Mathematically, meters per second squared. Done. I love this. I love this. I love this. Question. I hope we're still on question 2, just trying to explain a whole lot of concept. Please rewind and listen to what I've explained over and over again. All right, because I have so much to explain, and time. I don't want the video to be too heavy so that you don't get bored. So I'm going to stop at probably question 4, then part 2 again. We'll start from 5 up to the end. If I need to break it into 3 parts, I will, because there's so much I want to explain here again. I want you to do something. Now, do you notice what we've done here? Velocity and time. All right? Velocity and time. What we did was I want you to do this. Whenever you see a graph, this is dealing with a graph right now. When you deal with a graph, I want you to do 2 things. Number 1, multiply your axis. Now, if I multiply what's on my y, which is y, times x, let's check this. In this case, it's velocity times time. Does this formula exist? Let's go check something. Does this formula exist? What is velocity? If you remember grade 10, it is displacement over time. We explained a whole lot of this now. Displacement. Okay, let's cross multiply. Displacement now would be equal to what? Velocity multiplied by time. Oh my God, so it exists. So if we multiply the axis, it does exist. What does this now mean? It means that if the multiplication exists, what do? I find the area of the shape. Find the area of the shape. In this case, what is the area of the shape? Do you see something like this now? This is a trapezium, and I can break this into 2. Length times breadth, half base times height. Multiply the 2 areas. So we are saying the area here would give us the displacement. I'll summarize this in a table when I'm done just now. All right. And number 2, what do? Divide. Divide y over x. Already you see that this is changing y and changing x, which is what? Our gradient. Okay, if I were to divide, it would be changing v over changing t. Does this formula exist? Let's go to our equations of motion. Vf equals to vi plus a delta t. Let's bring this one over because I'm looking for that. So it's Vf minus Vi equals to a delta t. By the way, what is this? Delta V, right? Equals to a delta t. Can we divide both sides by delta t? And I'm going to actually show you something here again now. All right. So what do I have? A equals to delta V over delta t. Does this formula exist? Now, this is the formula we wanted. All right. This is the formula we wanted. So if we divide, we want this, which is equal to acceleration. That means the gradient is acceleration. You need this for all your graph questions. So for this one, I'm going to tell you something quickly on this. Let me tell you something on this, how to define. Every time you divide by time, you can call it rate. All right? And what do we know here? This is what? Change of velocity. So what is acceleration? So if you forget your definitions, run to your formula page. Acceleration is the rate of change of velocity. That's your definition from a formula. You're done. All right, great. So we say in here, under a VT graph, what do we know? The area of the graph gives us displacement. And the gradient of the graph would give us what? Acceleration due to gravity. All right, very important concepts there. Now let's try to answer the question quickly. Number 1, 3.3.1. Calculate the height from which the ball is thrown. It is always easy when you write down the given data. We're going to try to look at so many options here. And this is what makes this video quite lengthy, but of quality. What do we know? Downward. Downward as positive. What's my initial velocity? 10. Question says the height from which the ball was thrown. All right. Down v is positive 10. Okay, vector quantity. What do you know? It reaches the ground. Final velocity now is what? 29,6. Again, it's positive because it's going down. Remember the graph we had. The graph we had looked like this. I'll just do the first section. All right. Okay. Now, what do we know? Between the time from where I'm looking for where it was thrown to the ground. So I'm dealing with just this section. And this time frame is 2. Time is 2 seconds. I'm looking for height, which is delta y. Now, this is where you run to your formula page and get the correct formula. Now, what formula do you see here? If you go to your formula page, you can actually use any. Let's try option 1. Let's check something. Vf squared equals to Vi squared plus 2a delta y. Can we use this? Yes. All right. So what's my Vf? My Vf is what? 29,6 squared. What's my initial? 10 squared plus 2. Oh, by the way, what is my acceleration? Remember, it's down. So it's positive. 9, what? 8. I have 9, 8, and I have delta y. Awesome. Please get your calculators and walk through. I'm forced to go to the next page here. I'm forced to go to the next page. All right. I'm forced to go to the next page. Okay. All right. New page. We said 29,6 squared equals to 10 squared plus 2, 9, please guys, don't use delta x here. This is not horizontal. If it's horizontal, you cannot use 9,8. That's wrong. All right. So what would this be? 29,6. I'm sure you have your calculators. All right. Equals to 100 plus 19,6 delta y. Now we bring this here. It becomes 29,6 squared minus 100 equals to 19,6 delta y. All right. If you solve this now, we're solving. Please solve and do the maths. All right, what are you going to have? Because, okay, let's jump. Can we divide both sides by 19,6? All right. Now, if you do the calculation very well, you should now have, I don't know if my calculator is actually showing on the screen there, but I hope it shows. All right, I should now have what? 29,6 squared minus 100, all right, and that gives me 776,16, 776,16, 776,16. I hope you're getting that as well. Divided by 19,6 equals to delta y, all right, equals to delta y, divided by 19,6. What do you have? On my calculator, I have 39,6, and I hope that's what you have as well. Delta y is 39,6 meters. Good. Now that's just one option, because from the formula, if you go back to your data that you have written down as well, I can also use delta y equals to vi delta t plus a delta t squared. I'm looking for delta y. I know my initial velocity is 10. My time is 2 plus half, 9,8. My time is 2 squared. Put this on your calculator straight. You're going to have 39,6 meters. Again, it's 1 mark, and 1 mark. It's 3 marks. All right? Awesome. By the way, can I use my area formula? Can I use my area formula? We said displacement is equal to area under the graph. Let's see how this works. Look at my graph. Here is my, because I'm dealing with 2 seconds. I'm dealing with 2 seconds. So I can break that into 2. So this is half base times height, and this is length times breadth. So area is half base times height plus length times breadth, which is half. What is the base? 2. All right, 2. Now, what is the height? I'm looking at this triangle now. The height is going to be 19,6, which is 29,6 minus 10. So I have what? 19,6 there. Plus, now let's look at the rectangle. This is what? 2. And this height is 10. 2 multiplied by 10. If you do all of this, you're going to have that 19,6 plus 20. And that gives you what? 39,6 meters. Boom, done. Because sometimes examiners will say without the equation of motion. Guys, we do have a trapezium there. Let me cut this. If you are such a mathematics genius, you should know that the area of a trapezium, all right, now this is, if you know your mathematics very well, is equal to half, all right, because it's a combination of the two, and the breadth is common. Half, which is my length plus the height with a common breadth, and that will be half 10 plus 29,6. My base is 2, because this formula is just the same, you know, like what we did earlier on, and this is going to give me that again, and gives me 39,6 meters. This is the area of a trapezium, all right, which is awesome. Now you can We have different ways of getting that question done. Let's look at 3.4.2. We're already on an hour mark. 3.4.2. The question says, calculate time t shown on the graph. Calculate time t shown on the graph. Calculate time t shown on the graph. All right, calculate time t shown on the graph. Okay, let me bring the graph close. T. What do you notice about t? T is the final here. Now, there's so many ways to also do this. There's so many ways. Now, I can work with this from here. What's my initial velocity there? My initial velocity is negative 25. Initial velocity is negative what? 25. At t, t is the maximum height. Velocity is what? 0. Final velocity is what? 0. I'm looking for the time there. T is unknown. Remember my acceleration. Please don't change the value. It's positive. Do you see a formula here? Vf equals to Vi plus a delta t. 0 equals to negative 25 plus 9,8 delta t. If we move the 25, it becomes positive. Guys, you must never get a negative time. Divide 25 divided by 9,8. Your answer should now be, if you use your calculator, 2,55 seconds. But hold on. The time frame, we started from here. Now, this is where learners don't get. We started from here and we ended here. It means the time frame between these 2 points is now 2,55. So what is the time at t? If the time from the beginning to this place is 8 plus an extra 2,55. So t now is 8 plus 2,55, and that gives us what? 10,55 what? Seconds. Done. Beautiful there. Beautiful. All right. That's one way. I hope you got that. So please be careful of not forgetting the 2,55 addition. All right. Again, let's try something here. I do know my VF, all right, 0. I do know my VI, negative what? Negative 25. And my A, again, is what? 9,8. All right. If we were to work out something else, can we work out something else? All right. By now saying that VF squared equals to Vi squared plus 2a delta y. Again, don't use delta x. All right? Don't use delta x. What is going to be, what am I looking for here? I can look for my delta y. My Vf is 0 squared, negative 25 squared, plus 2, 9,8. Guys, remember I am dealing with, let me clean this again. I am dealing with these velocities. So whatever I get must be within this frame. All right. So what am I going to have here? 0 equals to 25 times 25 should give us 625. All right. Let's confirm that 25 times 25. All right. 25. So you have your calculator. Please confirm. All right. But we must learn these things, some of these things, just by heart there. All right. 25 squared gives us 625. All right. 625 plus 19,6, all right, delta y. All right, remember this is negative. My velocity is negative there. Okay, so when I move this over, I'm going to have negative what? 625 equals to 19,6 delta y. If we divide both sides by 19,6, what are we going to get? Divided by, okay, I'm with my calculator, divided by 19,6. All right, what am I getting? I'm getting, okay, 625 divided by 19,6. I'm actually getting 31,88. All right, 31. Guys, if we don't round off, this is not our final answer. 31,88. It's a long number, 887. All right, let's keep that answer that way. But that's not what I'm looking for. Now I have my delta y. I'm looking for time. Delta y, there's a formula again that says vi plus vf over 2. This is quite a bit long, but it will still get your answer. 31,887 equals to, what's my initial velocity? My initial velocity now is what? 25, all right, negative 25 plus 0 over my time frame. I'm looking for that time frame there. I'm looking for that time frame there. Now, if we cross multiply 31, now remember you have that answer stored on your calculator. Just multiply that by 2. Multiply that by 2. 3,775. 63,775. 63,775. Okay, let's go check something there. Do we have that there? All right, by the way, it is negative. We forgot here, it's negative. All right, the signs can be very, very disturbing sometimes. All right, so it is negative. So I'm going to have negative 63, remember I still a long answer, don't round off. All right, equals to negative 25 delta t. We divide both sides by negative 25. Now you go back to your calculator, your answer is still stored. You just say divided by negative 25. Divided by negative 25. All right, divided by negative 25. What are we going to get? 2,55. Awesome. Physics is beautiful. 2,55. But remember that t again, just the same explanation. 2,55 would give us what? 10,55 what? Seconds. All right. Spending so much time on this, and this is just lovely. Hold on. I do have a slope here again. Another option. I do have a slope here. Let's make this point 1 and this point 2. What is my gradient? y2 minus y1 over x2 minus x1. Remember now I can say it's v2 because it's velocity minus v1 over what? t2 minus t1. Okay, my gradient already from question number 3.2, acceleration, positive. So positive 9,8. What is my v2? You see, this is my point 2, and velocity is what? 0 minus, what's my v1? Negative 25 over, what's my x2? That's where t is. Minus, what's my t1? My t1 is 8. All right, my t1 is 8. What do we know here? Let's check. Now remember here, this is now direct. 9,8 equals to 25 over t minus 8. We can now cross multiply. T minus 8 multiplied by 9,8 equals to 25. Let's make our maths very easy. Divide both sides by 9,8. What are we going to get? I'm going to run to my calculator quickly and get me an answer. All right. 25 divided by 9,8. 25, oh, I said, okay, 25 divided by 9,8 would give me 2,55. All right, so t minus 8 equals to 2,55. What is t? We bring that over. 2,55 plus 8, and that gives us 10,55. Look at so many options in getting our correct answer. All right, we need to round off this video quickly, but we need to finish this. We need to finish this. All right, because it's 1 hour already. Okay, let's quickly deal with this question now. 3.4.1. The time in contact with the ground. Time in contact with the ground. Your answer lies there. It hits the ground after 2 seconds and leaves after 2,2 seconds. So what's the time spent? 2,2 minus 2, 0,2 seconds. We're done. Time at which the ball reaches the maximum height. Where is the maximum height? At maximum height, velocity equals to 0. After the first bounce, the ball bounces here. This is my maximum height, point D, if you go back to the graph. So what's my time? My time now is what? 4,955 seconds. Value of x. Where is x? There. We can do this mathematically, and if you understand your vertical projectile motion, you can actually work this out. All right? You can work this out if you understand. Okay. Now, if you understand vertical projectile motion, your graph should be symmetrical. If it's 27 here, it should be negative 27 here, because it leaves the ground. Sorry, it leaves the ground at 27, and because it's a free fall, it must reach the ground again at the same velocity. So same height, same velocity, all right, and the same time. Okay, but if you want to prove that, we can do that mathematically by considering this gradient again. M equals to V2 minus V1 over T2 minus T1. I'm sure that makes sense to you now. Point 1 and point 2. All right. So what's my V2? 27 minus, what is my V1? X over. What is my T2? 7,71 minus, what's my T1? 2,2. Remember, my gradient is positive, 9,8. All right, let's subtract and cross multiply. I'm going to run to my calculator just like you, all right, and follow through the voice instructions. It is 7,71 minus 2,2. So are you doing the same? Minus 2,2. What do you have? You have 5,551. Cross multiply with 9,8. What do you have? You have 53,998. 53,998 equals to 27 minus x. Can we move this over here and subtract? So what are we going to have if you subtract that? Now let's be smart. Just press minus 27. What are you getting on your calculator? 26,998. 26,998 equals to negative x. Equals to negative x. All right. So what is x going to be? X will be equal to negative 26,998, which is equals to negative what? 27 meters per second. You must understand vertical projectile motion, symmetry. All right, symmetry. It leaves the ground. These velocities must be the same because it's a free fall. All right. So if this is 27, this is going to be, this is negative 27 because it's going up. It's negative. Coming down is must hit the ground. 27, a symmetrical graph. All right, the time from here to the maximum height is the same time from the maximum height to the same level. All right, so we have that there. Last question for this session. All right, last question for this session. Is the collision elastic or inelastic? Give a reason. Guys, when you talk about elastic, now we're talking about velocity, or basically we're talking about kinetic energy. When do we talk about elastic collisions? When do we talk about elastic collisions? What do we mean when we say elastic collisions? All right, we'll do this again under momentum, but we know that one thing, kinetic energy must remain what? The same, must be the same. If we say kinetic energy, remember the formula, EK equals to what? Half mv squared. For this to be the same, this must be the same. But what do we notice when it hits the ground? It actually hits the ground. All right, look at this question here. It hits the ground. Let me go back to the graph quickly. I just wanted to see. All right, it hits the ground at 29,6, but it hits the ground at 27, the speed. So it's not. How do we now answer this question quickly? We now say that it is an inelastic collision. It is an inelastic. Hey, my screen just went blank on me. Is in all right. Apologies, my board just went blank on me. It is an inelastic collision, all right? And how do you write that down? It is inelastic because velocity is not the same, all right? The speed at which it strikes and leaves the ground are not the same, all right? It strikes the ground with a different velocity and leaves the ground with a different velocity. Hence, kinetic energy is not conserved. And that's why the ball did not reach the same maximum height like it did. All right, we will stop here for this session and continue from 4 to the end. I hope this session has been pretty exciting for you. A lot of understanding on the things that we need to understand. All right, join us again. This is Krazifizix. This is Bishop signing out. Thank you.